Hello, good afternoon everyone. Welcome to Liquid Brain. So today I want to present a small workshop on how you can use R and RStudio to connect the data directly from the TCGA databases, run it into R, and then use a simple neural network to do a biomarkers identifications on the data that you just downloaded. So there are a few things you will need for this workshop. First of all, you will need R installed, obviously. You also need to have RStudio as IDE. So you can use any kind of RD of your choice, but I'm just more familiar, so I prefer RStudio. So beside these two, you also need actually a large library of packages to install from both CRAN and Bioconductor. So I'll show you how to install them later. You also need to install Miniconda and Python through that because we are running Keras and TensorFlow, which currently do not have direct native run in R. So we actually need to run Python through R and RStudio. So the whole script will take about 30 to 45 minutes of runtime, depends on the speed of your computer, and particularly important if you have more than 8 GB of RAM and you do not have that, it's perfectly fine. Just make sure you don't have anything else running in the background, otherwise it's going to take a lot of time. So the exact script will be in the video description down below. You can go to my GitHub page and download the RMD file and you should be good to go. There's no other thing that you need to download beside that. So the hypothesis here is that gene expression is directly related to the Gleason score, which what I'm going to tell you what it is later on. And the gene will be regulated differently, depends on the severity of the cancer, and we should be able to use a neural network to actually tell the patterns and actually understand what are the genes that is going to behave differently in different cancer group. So why don't we use differentially expressed gene to do that if that is the traditional and most common way of doing so? Because in pattern 3, 4, and 5 in terms of Gleason score, there's no clear pattern of sample between them. So if you just run a DEG, it's likely that you're not going to get any significant differences between the different sample group because there's so many overlaps between the gene expression patterns. Okay, so what is actually Gleason grading system, as we talked about just now? It's actually just a simple grading system used to determine the aggressiveness of prostate cancer. So the grading system can be used to choose appropriate treatment options and just to scale the patient on how bad it is at the current moment, with 1 being no prostate cancer symptom at all, and 5 being just really bad condition for the prostate cancer and it's completely differentiated, and so on. So when we expect from the TCGA databases, we expect to be about 3, 4, and 5, and 3, 4, and 5, not 1 and 2, because 1 and 2 are usually not classified as the cancer. Okay, so there'll be 3 major sections to the code before we move forward. Section 1 will be just how do you download the data from TCGA, what are the packages you need to install, and some cleaning of the structure of the data before we go into neural network. Or section 2 will be a little bit more technical, where it will be the construction of the neural network. In this case, we are using a multi-layer perceptron, and then how do we actually get the data, train the neural network with our data, and then we're going to actually extract the model weights based on layer 1, based on their weight and bias, and actually extract the gene based on the value of weighted bias that we have actually identified from the previous section. Okay, so once we're done that, they should give us a list of gene of interest, GOI, which we're going to do like a simple conversion of the gene ID, and we actually run a gene set enrichment analysis of the GOI to see what kind of pathway are they actually involved, and so on and so forth. Okay, so just a disclaimer before we start, I wrote the whole project in about 2 days and I used another 1 day for the training and optimization of the network size and parameters. I don't think you'll be able to use exact detail that I use in your research, as well as why are we using neural network to run Gleason score. Kind of doesn't make any sense. However, focus on the understanding of the concept and the machine learning, and how would you be able to adapt this code directly for any kind of future planning that you need to do. Here we're presenting kind of a template situation. So if you do have a research idea you want to continue, I hope that you'll be able to benefit from this code. So for now, you can go to GitHub and download the code, and we'll meet you on the other side with the RStudio. Okay, so once you have downloaded the code and open RStudio, you should be greeted with something like that, where you have something in the top as a title, author and date, and you have individual chunks of code below. So this is actually called a format called R Markdown. So it might be slightly different from the R script that you are normally familiar with. So the only difference is the R script contains now in chunk, which you can easily run the whole chunk by pressing the play button right here. So the first chunk is always just a simple static when I want to output my R Markdown into HTML PDF. So you should just ignore it. But the line 10 over here is a line that I usually include in the beginning. So it will actually clear every single object in the current environment that I have, just to prevent cross-contamination between projects. Okay, so once you've done that, there are a lot of library that we'll be using right here. So there'll be two places you need to download the library from if it doesn't exist. So the first one is CRAN, the something R archive network. So you can just, so for example, if you want to do something like GLMnet, you can just key it in here. If it exists, means you'll be able to download the code directly from CRAN. So that's the easy part. For some of the library over here, for example, Summary Experiment, it doesn't actually come from CRAN because it comes from a separate repository called Bioconductor. So for those, you can actually just run the code right here for 31 until 34, which will install both BioC Manager, Bioconductor Manager, and they'll use Bioconductor Manager to actually install the Summarize Experiment package like that. So the easiest way, just go and try to find CRAN for all of them. And if you cannot find a certain package inside CRAN, most likely you'll be in Bioconductor and you will be able to run the code right here to install that. Okay, so the first step we're going to do is try to understand how to download data from TCGA, the Cancer Genomic Atlas, which is just a database for a lot of single cell sequencing for a lot of cancer patients. The nice things about that is it doesn't just have their gene expression, but it also have their clinical profile directly. So you can get a list of the projects that they have by running a get GDC projects functions, and you can actually narrate down by just getting a project summary of specific ID. So in this case, I'm focusing on prostate cancer, so PRAD. So actually you can see a little bit deeper into the data category and case count and file count of these specific projects. Okay, so once we figure out what kind of data do we want, we can actually use a little bit more information to download that. It is necessary in this case that you include as much information as you can in the beginning, so you don't over download the data and end up just clogging up your R so that you don't have enough RAM. So how do you know that is you can actually do try and error right here, which is actually not the good way. So I've included a website right here. Actually, let's go and have a look. So if you don't want to go through the command line to figure out what kind of data category and what kind of selection do they have, I think the GDC data portal is a good way. For example, I'm using a project ID of TCGA PRAD. So you have other IDs for some other project. I'll actually show you how later. So once you actually figure it out, the project, you can go to their repository right here, and you can easily find all the cases, for example, and you can find all the ID right here. For example, the data category, data type, experimental strategy, workflow type, data format, platforms, and all the barcoding that you want as their case ID. Okay, so this is where I put my project, data category, data type, experimental strategy, and their barcode. So I did not actually include a specific barcode right here because I have enough RAM to run. But if you do not have enough RAM to run this analysis, you can go to barcode, for example, just put, for example, an AF right here, or CJ or AG. So that should narrow down enough so that your computer will be able to run. So after you have select the parameters that you want, they'll go into an object called query TCGA, which is just a simple line of code to download the data using the GDC download. So here, the file per chunk is important because if you do have a very fast internet, you can get a faster file per chunk or bigger file per chunk, so you can download more files at the same time. But if you have a slow internet like me, so you might want to reduce the file per chunk so that in case that the download actually get interrupted halfway, you don't have to download as many files that you have. So GDC download only happens the first time when you run it. After you have actually downloaded the file, you don't have to download this again, and it should actually launch directly on your computer using the pre-downloaded file. So after you downloaded everything, this is one code that's going to take you a lot of time, which is called GDC prepare. So from above, we have downloaded all the file necessary. So GDC prepare just takes all the file and actually make them into a summarized experiment object. So to know more about summarized experiment object, I actually make a video about that. I'm going to put it in a bubble right here for people that are interested to know more. But what you need to know is that it's actually just all the experiment into a single object so that we can actually navigate them much easily compared to just putting it as a data frame. Okay, so you can see that in the query, the class query TCGA is going to actually end up as a, oops, it doesn't work. So let me just do that. So yeah, it doesn't work right here, but it's a summarized experiment object. So it's actually just why do I do a TCGA data? So it should be right here. So yeah, I believe there's some mistake in the code here. So if you run this should actually do a range summarized experiment object. So once you have that, we need to actually do a save RDS. So what does this actually do is that it will save whatever that you have prepared just now into a RDS object, which is like a data object specific to R, where it will, even if you lost all the files right here, if your computer just shut down suddenly, you can still resume your session by just loading the RDS or the read RDS function, so you can recover the object directly. You can also carry this object from one computer to another very easily. I specifically recommend this because GDC prepare takes about 10 to 15 minutes, and if you're gonna run 10 to 15 minutes every time you shut down, I think it will take a much longer time for you to finish up the project. Okay, so after you have done this, you should have an object called TCGA data, which is actually in here, a range summarized experiment object. Okay, so it's actually quite nice for us to have a look right here. Actually have a look at our TCGA object. Okay, so in TCGA object, just remember there is always an assay. So an assay contains your expression data in a big table. Column data contain all your sample data. For example, what is the barcode name, what is the patient's, what is the Gleason score, type of tumor, and so on. There's also the row ranges, which actually contains all the name of all the genes that we have actually do one by one, what chromosome they are referring to, the strand they're referring to, and so on and so forth. So everything about the gene goes to the raw data, everything about the sample goes to the column data, and the gene expression data is stored in the assay. So that's the basic structure that you need to know. So when we have done that, we actually need to prepare our data to be data frames suitable for the Keras and TensorFlow neural network input. So what I do here is, first of all, I just code it into a SCDF object. So why do I want to do that, and why I want to duplicate the file is because every time I try to do this, when I actually accidentally, I will actually kill my TCGA data. So it actually ends up that I have to rerun the GDC prepare or reload the model from an RDS file, which is very, very slow. Sorry, reload the object from the RDS file, which actually takes a long time. So I usually just duplicate as SC object as a temporary object. And after I have done with all of them, I'm actually gonna remove the object right here. No, I'm not removing, but I'm removing the TCGA data right here so that I don't end up with the duplication of object that hogs up my RAM, but also I don't actually end up destroying my original data before I've actually done using that. Okay, so what I do over here is, first of all, remove the metastatic prostate cancer, because there's only one of them out of the 553. So I do not want them, so that it's easier for me to identify the two different sample group. So if it's have a metastatic, the usual outlier, and it is kind of harder for the differentiation for the neural network later. I also restrict my data to first 550 of them. Specifically, when I train it, I want a batch size of about 25 or 50, so that I don't end up with one more cycle of training with not enough data. So I try to make it a full number. Not recommended if you don't have enough sample to throw away, but in this case, I have more than enough. So I'm gonna do that. So the next one is a gene list and a sample list. As I said just now in the SE object, the row ranges contains all the gene and gene ID, which is, I'm gonna extract the gene ID here, which is actually an ensemble ID. So gene ID, you can actually have a look somewhere here. Yep. Okay, so you can actually see this is the list of ensemble ID that actually we have extracted out from the IC object. And we can have a sample list which actually contain all the name of the barcode of the patients that we have. So this is just temporary situation, not strictly necessary. So the next one is actually extract out the experimental data using a TPM on strand. So for those that are not familiar, TPM is kind of a normalized count data. So it's already done all the normalization for me, so I don't have to do it myself. However, if you're running things like DEG or limma, you might want to actually use the raw count. So this is not suitable for you. But I'll use this one because I'm using a neural network and it's actually easier for me to train them. So once I've done that, I'm actually gonna put my gene list and sample name, which is exactly the same thing here, into my EXPR, which is my expression matrix. And I'm gonna do a filtering of expression matrix to filter out genes that have been expressed more than 2,000 times. 2,000 TPM. So why do I do that is because if the gene expression is too high, most likely they're housekeeping gene and they're not very useful for me to differentiate between my different cancer Gleason score. So I'm going to throw them away, and they might also explode my neural network. So I do not want to include all those housekeeping gene that I have. I'm also going to exclude all the gene that have a count radar of less than 100 maximum. So because they're just too low, I don't want to, it's really hard for them to actually make any significant contribution to my neural network. So I'm also gonna actually exclude them. So high and low, I'm gonna do high pass and low pass. So I only take out the middle part. So as you can see from the EXPR filter, I only left with about 5,000 gene with 550 patients. So that's not a lot, and it is not a lot for a reason because I don't have a lot of RAM. So if you can go for 10,000, 20,000, 30,000, good for you, but I'm not going to show you how to do it right here. Feel free to adjust the filter on the number here based on the sample and try out different rate and to see if that works for you. Okay, so once we have done the EXPR filter, it should be something right here. Where are you? Yeah, here. So it's going to be a really huge matrix with the column data as a sample ID, as a row data with my gene ID, and all the TPM count right here. And it should be somewhat normally distributed. If not, we're going to do something to them later. So how do you actually visualize sample relationship? It's actually through something called PlotMDS. It's actually come from the limma HR package called plot multi-dimensional scaling. So what that means is that you will be able to take a multi-dimensional data, in this case 5,000 different genes, and try to find a relationship between them and try to plot out the distance between each of the sample based on their correlation to each other. Mathematically quite complicated. So I'm not going to explain it right here, but also I'm not going to run it in this case because it's way too big for my computer to run, and I just do not have enough RAM for the vector size. So if you have a smaller data size, feel free to, I'm going to leave it here with a library here so that people that want to have a look can have a look, especially if you have enough RAM to run it, otherwise it won't run. So I think I need 27 gigabyte of RAM for this to run, otherwise it won't. Okay, so once I'm done, I'm gonna actually do a min-max normalization plus log2 normalization. So what that min-max normalization means is the lowest count rate in my sample is gonna be assigned as a 0, and the highest count rate is gonna assign as a 1, so that everything goes between 0 and 1, which is what we call min-max normalization. And I'm also gonna run a log2 normalization so that the data is a little bit more normally distributed. Otherwise, for gene expression, they are more skewed to the negative side, so it's not that great. So I'm gonna leave the normalize in min-max normalization code right here, but in this specific data set, after my try for the whole day, I realized that it doesn't actually work that well if I'm using a min-max normalization data, and it's actually much better that I just use my raw data directly. So after several trying, I actually removed the normalization because it works better on the training. I've also removed the copy data function. So why does it exist here? Because in certain situation, when you have small enough sample, you don't want to, for example, ask your neural network to train on 20 samples per epoch. Right, you want it to duplicate itself, so maybe you duplicate the data by 10 times, so every time it's able to look at in single epoch they're able to look at the same 20 sample 20 times and so on and so forth. So there's a larger time for the machine to learn per epoch. It usually results in things being more accurate and more stable. Otherwise, it's just gonna training go up and down and get very confused. So this is why I leave it here, but I'm not gonna run it right here. So it's actually supposed to, yeah, it exists right here like that. Okay, so for those that have a small sample that want to experiment more, this is how you can do it. But in this case, I'm going to do a simple transpose and then run a log2 normalization and change the dimension of our trained data into a different way. So why do I need to transpose? Because in the, what is that called? In Keras, they actually want the sample to go on the other side compared to how we do it in the summarized experiment object. So the gene becomes the column and the sample becomes the row and so on and so forth. So which is why the T function is here, which actually stands for transpose. So after that, I also run a histogram for the tree. So you can actually see the histogram of the 3 different sample and their gene expression in overall. So it's actually kind of normally distributed, so which is what I want. So I want to be able to see most of them. So the last one I do is actually a dimension, just to check if it's the correct way. I have 550 patients and 5,899 genes, so that I can actually use this data now to prepare my train label down there. But before I do that, I'm gonna run a principal component analysis, which is very similar to the multidimensional scaling over there. It's just to visualize the individual sample differences between one another using a way of how to compress different dimensions. So in this case, we actually have 5,899 dimensions because that's the number of genes that we have. So principal component analysis just squeeze those down into 2 dimensions and plot them out into a plot that we can see. So this is exactly what I anticipated, and this is actually why I choose to do this analysis, because secondary Gleason's grade has absolutely no trend and no clustering, so it's very hard for any common statistical tool to find it. But hopefully machine learning can do a little bit of pattern recognition on this messy data that we have right here. Okay, so now it's actually the train label. So because it's a categorical data that we see just now, pattern 3, 4, and 5, we're actually going to do something called a one-hot encoding. So what that means is actually, let's do it one by one. So as you can see, the first thing is to extract the secondary Gleason score, and we convert it to a factor and then to a numeric. So what that actually means is that in the train label here, you can see it's a character of pattern 3, 4, 5, 3, 4, 5, 3, 4, 5, and so on is stored as a string. So it's hard to a machine to understand what is a string. So a factor will be able to take all these different patterns and assign 1 to pattern 3, 2 to pattern 4, and 3 to pattern 5. So it's much faster for the computer to calculate as factors. But beside that, I'm also going to convert my 1, 2, 3 into a numeric 1, 2, 3. So my train level can simply exist as a list of 1, 2, and 3. But because Keras actually is actually based in Python, so in Python arrays start from 0, so I actually have to minus 1 off, so it becomes a list of 0, 1, and 2. So 0 maybe is pattern 3, 1 is pattern 4, and 2 is pattern 5, and so on and so forth. And then I'm gonna restructure them into a 2-dimensional matrix. Sorry, 2-dimensional matrix like this, with 550 rows. Each of them represent their sample type of 0, 1, and 2, which stand for pattern 3, 4, and 5. So once I'm done, I'm going to use this very useful function from Keras called toCategorical. So because the problem with neural network is that they like to go between 0 and 1. So we don't want to have 2 and 3 and 1 and 2 over here. So we're going to convert our 0, 1, 2 into 3 separate columns. So if it's a 0, put a 1 in column 1. If it's a 1, put a 1 in column 2. If it's a 2, put a 1 in column 3. So we are basically expanded our dimension of our matrix. Actually, yeah, a list into a matrix, but it is much easier because now it only has 0 and 1. So it's much easier for a neural network to understand and interpret this. And the last one, we're gonna just run a p-heat map to actually visualize how many 0, 1, 2, and 0, 1, and 2 that we have. You can see pattern 4 is the most popular, pattern 3 and 5, it's around that. So you can also see from right here where pattern 4 is the most common among all our samples right here, but it's quite a good spread of what we have overall. So we can also see right here we have 170 pattern 3, 267 pattern 4, and 115 pattern 5. So this is great to have a slightly equal distribution of different patterns. Otherwise, if you do a 90-10 classification, machine learning network will always just throw everything into the 90%, and it's very hard to get through it. Yeah, so having this kind of equal thing is great. So this is basically the end of section 1. So what we have now, we have a trained data. You can see here is a large matrix with the correct dimension, which is 550 times the number of gene. And we also have, the train label here, which is 550 times 3. Okay, so this is the data that we're going to go into our machine learning or neural network to train. So this is where we go into our section 2, which is constructing a neural network and training and extracting the weight and bias. Okay, so if you're tired, maybe take a break, have a drink, and then we'll come back to section 2. So I'm just going to continue because this is obviously a video recording. So how do we construct a neural network? Is actually to Keras and TensorFlow, which is actually very simple after you have loaded in the library as you have done from above. So I always done the first thing is to remove a model, because when I retrain a model, I do not want the previous model to contaminate my next model. So a remove model, just remember, remove whatever that I trained last time. So because if it doesn't exist, it will just say not found, but the code at least will still run. So the second is the dimension of the trained data. So this is actually important because it allows me to understand how many genes I have, because how many genes I have is the number of input neurons I need to assign to. So in this case, it's 5,899. So I know that, so that when I'm doing my neural network array, I have to assign a neural number, a node number that is close to the trained data over here. So this is where my network comes in. So actually the last one here is not necessary. So my network actually have 5 dense layers with an input and an output. So the first layer will be 4,000 neurons big, then 2,000 and 1,500. And I'm going to pipe the last one to 3 neurons representing pattern 3, pattern 4, and pattern 5. So how do you construct a network? Is actually just like that. So first thing is, what kind of model do I want? In this case, I want a sequential model, because models, the data goes in one side and come out on another in a sequential pattern. So there's a sequential model. And the first layer will be a dense layer, which is just an interconnect layer with neurons connect to all of them on both sides. So the number of units is how many neurons do we want. In this case, it's 4,096 on the first layer. We're going to use a ReLU activation, rectified linear unit, if I'm not wrong, which is convert whatever positive as it is and negative into 0. And we're going to have our input shape as our dimensional data, which is 5899. So in this case, 5899 is being piped to 4096, to this one, to this one, to this one. And in the end, it's going to have a last dense layer of our output. In this case, I'm going to change the last layer to sigmoid, because remember, we're using one hot encoding. So in the end, we need either 0 or 1 and not anything in the middle, which is why everything in the middle, I'm using ReLU, so that it will just have that number, expression number goes one layer by one layer. But in the end, I want to try to sum it to either 0 or 1. So if it's 0.9, most likely you just get thrown to 1. If it's like 10.5, it's going to get squeezed to 1 as well. So it's just much easier for neural network to differentiate. So once you're done, you can actually just run a summary on the model, like so. I usually don't include it because I can actually see the model structure directly from the code. But if you need to, that's how you do it. And then once you're confirmed that your model is correct, we have shown the layer 1, 2, 3, 4, and layer 5 as the output, you can actually just do a model compile. So what does an optimizer means is that their learning rate or the way of they learn in the neural network. So how the neural network actually learns is every time they see a wrong data, they try to adjust the node a little bit so that it fits the way better. So how fast they adjust with compared to the the errors that it makes is gonna call the optimizer. So there's like SGD, the stochastic gradient descent, there's Adam, there's Ala Delta, and there's many other one. Not gonna go deep into it. I usually just go for SGD or Adam in this case. And the loss is actually just what is the difference between the predicted output and the actual true label, right? Binary cross entropy is very useful if everything is between 0 and 1. It's binary, 0 or 1. And they're going to compute the difference between the two and try to understand what is the losses from the predicted to the label, which is how far they are. And binary cross entropy is suitable for this situation. But if you have multiple classification, you want to use multiple cross entropy. And if you are running some sort of linear regression, for example, if your output is an H, for example, you might want to use mean square error or some other mean absolute error, for example. So the matrix will be something that is for you to refer to. In this case, accuracy is how accurate is my neural network model to predict the pattern 3, pattern 4, and pattern 5 that we have. So the loss is not equals to the matrix. They have a different calculation method and mathematics, but I believe the optimizer actually based the back propagation on its loss and not its matrix, but don't quote me on that, I don't remember. Okay, so once we done all the parameter settings and we're happy with all the parameter settings, is where we can start training the model using a model fit function with X being the input and Y being the output. Just make sure that your X has the correct dimension as your input layer. Oh no, the X is fine as your input layer, but your Y need to be correct. Your Y dimension need to be exactly as what you have over here. So your X and Y also have the same number of, for example, 550 and 550, they have to be the same. So epoch actually means how many times the data is trained again and again. So in this case, 200 means each time I'm doing 550 patients, I'm gonna do 200 times of that. So 200 times 550 is how many times the network actually sees the data. So use multiprocessing means, do I want to use parallel computing to speed up the process? If you have a lot of computing core, definitely. But if you have like fast computing core and your data is small, don't do that. So you can try both and see what happens. Batch size actually means how many times I want to throw the data into my network in each run. So in this case, each epoch, I'm going to trade 25 times, means that every time I'm going to fit in 550 divided by 25, which is about 5 or 10 patient data. And you can, of course, the larger batch size, you will learn faster, but more carelessly. If you have a smaller batch size, it will be more careful about each patient. But if your patient variation is too big, then it might actually waste a lot of time adjusting in and out. So again, try and error and see what you have. So the last one is validation split. So validation split actually means that I'm going to use, in this case, 0.1 means I'm going to use 90% of my data for training and 10% for testing. And then we'll actually check the training loss and validation loss to see if you're overfitting your data or underfitting your data, or if your model training is actually correct or not. So yeah, I'm not going to do it here because we're doing biomarkers selection, and I don't need the kind of generalization in our model training. So I'm fine to overfit, so I'm not going to put in the validation split, but I'm going to include in the code for anyone that's interested. Okay, so I'm not going to train it right here in front of you because it's going to take way too long, but feel free to adjust the epoch. I'll say start with 10, and if it's fine, then you increase further until, for me at least, I need actually 200 epoch to reach the kind of accuracy and loss that I'm happy with. So once I've done that, you can of course save your model as a HDF5 object, HDF5 file, so that again, if your R crashes, you don't lose the model that you just trained, and you can actually just manually load them in very easily after you have trained the model, and you can do evaluate to understand what are the loss and accuracy you have. So in this case, my loss is 0.1683 and my accuracy of the network is actually 90%. So I'm quite happy. 90% of the time, the network is able to choose the correct patterns based on the input gene expression data, based on the situation that I have. So it can be higher if you train longer, but I decided 90% is good enough, and I don't want to go for 400 epoch, and I also do not want my model to super overfit my data to a certain patient group, for example. Okay, so that's basically the neural network training part, and that is where things get a little bit, not a little bit, a lot more complicated in terms of weight and bias. So a little bit of background on neural network for those that are not familiar with. A neural network basically just take all the input, which is in this case, the input is the gene expression count. So the higher the count, the higher the input. So every single input will be times by a factor, in this case called a weight. And the 5,000 gene that we have is going to have 5,000 weights. They're going to times together and they're going to add everything together. And that is going to be added by a bias and for the single node in layer 1. Okay, that's how you do the calculation for first node in layer 1 of a neural network. So in the second node is exactly the same. 5,000 of them, 5,050 gene times by another 550 different weights for node 2, add them together, add a bias, and that's our value for node 2. So every single node is then actually times by the activation function to actually change the value to appropriate amount before they propagate into the next thing. But basically what you need to do is that we have 4,000 different nodes in layer 1. We're gonna do 5,000 times weight plus it in, 5,000 times weight plus it in 4,000 times, and so on during the network. Luckily our computer is really fast, so that we're able to train and calculate all this like automatically and understand that we're doing a matrix multiplication. The computer don't actually calculate nodes by one by one by one by one and so on. So once we've done that, we can actually extract the model in layer 1 and what is their weight and what is their bias by just running these two commands right here, which actually assign a weight and a bias. So a weight will be a big matrix of 5,899 times 4,096. So 4,096 because we have 4,096 nodes, and 5,000 because we have 5,000 gene. Remember, every single node has their individual weight for every single gene, which is why we have so many value. Okay, so however for bias is a bit more easy because every single node only have one bias, so we only have 4,000 data. So what I'm gonna do next is actually extract out the gene that actually cause the neuron to fire. So the neurons that is high in terms of their final value, that's gonna fire, and I'm gonna filter out those nodes and use those nodes again to figure out what gene actually causes them to fire. Very complicated, but this is the basic concept of it. So again, I'm gonna duplicate my train data into input data, and because I want to save some time in the computational, I'm only gonna select 100 of my patient to do what I described just now, which is choose the gene that is causing the neurons in layer 1 to fire. Okay, so why do I choose 100? Because I believe that the genes are not going to be that different between different patients. So I'm only going to randomly select 100 of them. Hopefully that will cover enough for me to reach my conclusion without wasting too much time and RAM space. So what I do later is, what I described just now. So total weights equals to the weights times the sample. And we're going to sum up every single nodes plus its bias. And we're gonna actually just C-bind them into object. So actually it will be easier for me to show you. Okay, so the total weight and bias is actually this. So this is 1, 2, 3, 4, 5, 6 is the node, and V1 is actually the final value exists inside those nodes. So if it's very low, means that in our ReLU activation function, it's gonna get slashed as 0. So we're gonna ignore them. But what we need to know is what are the highest nodes that it's gonna fire. So node 3139, 2382, 1237, 929, those are the nodes that's going to fire, and we're gonna actually isolate them. So once we figure out what are the top nodes that we have, which is any nodes that has more than, in this case, more than 1. So more than 1 based on ReLU, they're gonna fire. So I'm gonna filter out what are those that are more than 1, and I'm gonna fish out what are the genes that contribute the most to them. Okay, so I'm gonna create something called a gene to good nodes, which is actually just a total weights, which is all the weights filtered with only the number of nodes that we have. So we have looked at a goods node just now, right? So we have looked at a node is 12381117. So in this case, gene to good node is gonna have all the genes, but only the number of nodes that I want. So in this case, you can see there's a selection number of nodes that we have. Okay, so once we're done that, we're gonna actually go through the nodes one by one and extract the top 10 gene that is causing the nodes to be in that kind of high level of value. So we're gonna do it over and over and over again until we get a list of gene and then their frequency number. So we can actually have a look at our GOI table, which is after going through all the different nodes and all the different gene, what are the gene that appear many times that's causing all this thing to fire. Okay, so let's just run it one by one. So there should be something called GOI table right here. So we have 415 gene that appear a total of 20,000 times, 15,000 times, 12,000 times, and so on and so forth. So we know that these are the gene that is causing the node to fire, and it is likely that in the input, this gene has a high expression, so it is being carried over into layer 1. So there's some problem with that I'm going to discuss later on, but these are the gene that is in high frequency causing node 1 neurons to fire. So we can actually isolate them as our gene of interest. Okay, so that actually conclude our section 2, which is use a neural network, use the weight and bias of the neural network after training to actually figure out what are the list of genes that I want and their relative importance in the overall expression and so on. So now we have this table, and these are our potential biomarkers that we have. But you know, running gene by gene is kind of silly and it's kind of bad, and I'm using a cutoff. So I don't want to say absolutely these are correct. So what I'm going to do is actually something called gene set enrichment analysis, which actually moves us towards section 3 of this video or this workshop. So what I'm going to do is, because the cluster profiler, the package that I use, needs the interest ID to do the comparison. So what I'm going to do is, first of all, convert all the ensemble ID into interest ID. So in order to do that, we can't actually use like the .5, .8, .1, 2, and .9 because those are not really exist in our system. So we're going to remove them using a substitute function right here. So in gene list now is only the ensemble ID without whatever the behind the dot over there. So we're also going to use another library called orhseg.db, which is just a human annotation databases, and we're going to use a brtr function here to convert our ensemble ID to interest ID based on the database here, and we're going to drop those that are if we cannot map them, we're going to drop them, which is what you mean by drop equals to true. And then once you run that, they will actually tell you how many of them they have dropped, I believe here. Yep, so you can see that 3% of input failed to map, and there's some that actually map to duplicate, I believe, which is why from the 400 gene or 500 gene that we have just now, we actually dropped down to 428 different gene only. So that is our gene of interest inside our, what is that called, the enriched ID or the GOI that we have from our neural network. So in order to compare against or to run an enrichment analysis, we need to know what are the overall gene that we included in our first analysis. Because we have filtered off all the gene over a certain amount of expression, it is not fair to compare against all the genes that we have. So the second chunk over here is trying to do the same thing as above, but we are only converting all our genes that we fit into our network, which actually we go from 5,899, if I'm not wrong, down to 611. So 5% of the input are failed to map, which they cannot be mapped to the ID. So they're relatively low, so I don't see much problem with that. So we should be fine on that. So once we're done, we're gonna actually use the group goal and enrich goal to actually find, first of all, group goal is what are these genes doing over here. So try to figure out what are their different goal category that belongs in, and the enrich goal try to actually find the enrichment analysis based on the input and the overall universe of the gene list. So it's going to take a while, but you can actually see right here, I've done both, and I actually do a head ego BP, which is I'm only enriching the gold category of biological processes, and we're going to do the two other one below, but I'm only going to show the top 10 after the p-value and q-value cutoff of 0.1 and 0.5, and we're going to use actually something called Benjamin-Hodgman correction factor, which actually you can see more details in how it is done in our GSEA algorithm explained right up here, and I'll just put a bubble there if I remember. Okay, so once I'm done, I'm also gonna do a go plot, which actually visualize the data into a plot right here, and I'm gonna save the result as a CSV. So as you can see, these are the table that we have, and we can see in terms of their biological processes, the separation between the three Gleason score is related to their immune responses, their cytoplasmic translation, peptide biosynthetic, and respond to bacterium and immune response. Yes, they are actually related to cancer, but there's nothing specific that we can actually use. And if we map it down to it, you can actually see that because there's so many categories, it's kind of messy. But yeah, it's the same defense response to bacterium, translation, cytoplasmic translation, and peptide biosynthetic processes. So these are some of the things that you will need to look out for. But what could be the mechanism currently, I can't actually tell you because machine learning doesn't actually go that deep. So the same thing applies for here in terms of the molecular function enrichment score. You can actually see data frame here where the structure constituent ribosome, the structure, molecule activity, antigen binding. And something I find interesting is MHC class 1 and class 2 protein binding complex, which actually I found in some paper is very tightly related to the prostate cancer development. However, here also we don't have an understanding of whether this overexpression or underexpression is causing a different kind of Gleason score or not. But it's something that is definitely worth looking into. And yeah, I don't exactly know what contributes to that, and I'm not super experienced in terms of prostate cancer anyway. Okay, so you can see the similar concept where we can see, oops, right here. So yeah, the MHC proteins is here, the structural molecule activity, immunoglobulin, receptor binding is here, and they might contribute in their own way. Or not. I'm going to tell you why later. So similar thing can be found in the cellular category, where we find a lot of cytosolic ribosome again. And I don't know why it's blood microparticle, but it sounds interesting. And this again are the enrichment that is contributing to the Gleason score. So yeah, we can also see from the go plot just to visualize understanding, and you can find all of them are in fact related to the ribosome and ribosome biogenesis and ribosome metabolic system and biogenesis. So that brings it to the actual end of the workshop, where we actually find some pathway that's enriched, but there's a tons of issue in this case. So remember in the beginning, this is not meant for research, but rather a way of educating how TCGA data can be downloaded, manipulated, feed into MLP, and use MLP to reverse engineer a list of interests that you have. So a major issue that I think people that continue on project need to look out for, I only take layer 1 in terms of the bias, and it's unlikely that layer 1, so layer 1 contains a lot of noise, which layer 2, 3, 4, 5 actually filtered off. So if you are going deeper into this logic, please go in and try to figure out what are the weight in layer 2, layer 3, and layer 4, and how the data actually get cleaned up, because definitely we have a lot of noise over here, which I actually tried to filter some of the voice by just using the frequency table that we look at just now in terms of weights, get the weight inspection. So I actually filter off based on the frequency, but I don't think it's complete and I don't think it's great. So the second thing I can see here is we have 5,000 gene, remember, go to 4,000 nodes, 2,000 nodes, 1,500, and from these 500 nodes, it goes straight down to 3. So we also don't know what kind of thing has happened over here. So it is likely that a lot of them that goes through the layer 1 are not important at all, because they got filtered off on this 3 layer. And so we actually need to know what are the actual contributing factor that is inside the 512 layer that directly goes into the final output layer, which I have no way of actually go in and inspect or reverse engineer a way to actually figure out the gene and how to actually identify those genes out based on based on so many layers of deep learning. So I think there's a way to do it, but I only spent 3 days on it, and I'm planning to do more of it. But this is the current finding that I have, and I feel like it is enough to make a video. And for anyone that want to go more advanced, feel free to just send me an email, leave a comment down below, and let me know what other thing do you think I should explore further, or you are currently doing and you have problems with. So I've actually recently opened up a membership and a Patreon account. So for those people that wants to continue to see this kind of thing, because you know they're free on YouTube, I need to pay my rent somehow. So if you can, please contribute. And if you do need someone in the coaching on your analysis and setting up your machine, do let us know as well. So for now, I hope you enjoy the whole set today, which is going from TCGA going straight into neural network, and then go from neural network into genome interest, and then some enrichment protocol to finally get a result like this, which is blood microparticle, which is very interesting. Okay, that's all I kind of have to say for today. I want to say thank you for watching. Please do like, comment, and subscribe anything you can to boost the algorithm, so we can actually be seen by more people and help more people to figure this out. Okay, bye.